Right now, not in a movie, not in a simulation, there is a machine drifting through interstellar space. It was built by human hands, powered by decaying plutonium, and it has been completely alone for over 40 years. It is currently so far from Earth that a radio signal traveling at the speed of light takes more than 22 hours to reach it. 22 hours. And the strangest part? It's still talking to us. This is the story of Voyager 1, what it has already done, what it is doing right now, and what will happen to it long after every human being who ever lived is gone. Long after the sun is gone, long after the stars themselves go dark. Hold on, because the timeline of this story is going to break your brain. Before we talk about where Voyager 1 is going, we need to talk about why it exists at all. In the early 1960s, a young graduate student named Gary Flandreau was working at NASA's Jet Propulsion Laboratory. He was given a fairly routine assignment: plot the positions of the outer planets for the coming decades. What he found stopped him cold. In 1977, the outer planets, Jupiter, Saturn, Uranus, Neptune, would align in a configuration that happens once every 175 years. A configuration so rare and so precise that a single spacecraft could visit all four of them using something called a gravity assist, essentially letting each planet's gravitational pull slingshot the spacecraft to the next one for free. Miss the window, and the next opportunity wouldn't come until the year 2052. NASA moved fast. 2 spacecraft were built, Voyager 1 and Voyager 2. Voyager 1 launched on September 5, 1977. Paradoxically, it launched after Voyager 2, but on a faster, more aggressive trajectory. It wasn't designed to visit every planet. It was designed to get to the most important ones faster, and to do something at Saturn that would redirect its entire future. More on that in a moment. Both spacecraft carried instruments to measure magnetic fields, plasma, radiation, and charged particles. Both carried cameras capable of resolving detail that no telescope on Earth could match. And bolted to the side of each one was an object unlike anything ever put into space before or since, a 12-inch gold-plated copper disc, the Voyager Golden Record. Think about what it means to write a message for someone you will never meet. Someone who may not be human, someone who may not have ears or eyes or any framework for understanding what you are. That was the challenge given to a small committee led by the astronomer Carl Sagan in 1977. What they created is staggering. The record contains 115 images encoded in analog format, diagrams of human anatomy, mathematical concepts, the structure of DNA, scenes of daily life on Earth. It contains natural sounds: rain, wind, surf, thunder, birds, whales, a mother's first words to her newborn child. It contains music: Chuck Berry's Johnny B. Good, Beethoven's Fifth Symphony, Azerbaijani bagpipes, Javanese gamelan, a Navajo night chant. It contains greetings in 55 languages. In ancient Sumerian, a language no living person speaks fluently. In Mandarin, someone says, "Hope everyone's well. We are thinking about you all. Please come here to visit when you have time." And it includes a map etched directly into the record. pulsar map, a diagram using the known positions and frequencies of 14 pulsars, stable cosmic lighthouses, that any sufficiently advanced civilization could use to pinpoint exactly where in the galaxy this record came from. We didn't just send a message, we sent our address. Carl Sagan called the record a message in a bottle cast into the cosmic ocean. He meant it. The probability of any civilization ever finding it is by any rational calculation nearly zero. The galaxy is simply too large. But here is the part that stays with you. They sent it anyway. Because the act of sending it, of choosing what to include, of deciding what represents us, that act says something about who we are. About a species that, even knowing it would probably never be heard, wanted to be known. The record is still out there. It will survive longer than any building ever constructed. Longer than any book ever written. Longer, almost certainly, than our species itself. Voyager 1 reached Jupiter in March 1979, roughly 18 months after launch. Nothing about what it found was expected. Scientists knew Jupiter was big. They knew it had storms. They knew it had moons. What they did not know was that one of those moons was essentially a living geological engine. When Voyager's cameras resolved the surface of Io, a small moon slightly larger than Earth's, the navigation team noticed something in the images that didn't make sense. There was a faint, umbrella-shaped structure extending above the horizon. Navigator Linda Morabito was the first to catch it. It was a volcanic plume, active, erupting in real time. Io was not a dead rock. It was the most volcanically active body in the entire solar system, stretched and squeezed by Jupiter's tidal forces until its interior is continuously molten. Some of its plumes rise 300 kilometers into space. The surface temperature near certain vents exceeds 1,600 degrees Celsius. Nobody had predicted this. It rewrote the rules. And then there was Europa, a moon that appeared almost wrong in the images. Too smooth, too bright, covered in a lattice of dark cracks like the surface of a cracked eggshell. What those cracks suggested took years to confirm. Beneath Europa's icy crust, there may be an ocean of liquid water larger than all of Earth's oceans combined. An ocean in the outer solar system, kept liquid not by the sun, but by the same tidal forces tearing Io apart. Voyager 1 didn't land there. It couldn't, but its images planted a question that planetary scientists are still trying to answer. Is something alive in that ocean? Jupiter's gravity assist accelerated Voyager 1 by roughly 35,000 kilometers per hour. It bent the spacecraft's path and hurled it towards Saturn. Saturn, when Voyager arrived in November 1980, was a revelation. The rings, which from Earth looked like a simple flat band, turned out to be a dynamic, violent system of hundreds of individual ringlets, each one shaped by the gravitational tug of war between Saturn and its moons. Waves propagated across the rings like ripples on a pond. Gaps were carved with surgical precision by shepherd moons. The rings themselves, despite spanning hundreds of thousands of kilometers in width, are in some places less than 10 meters thick. But Voyager 1's most important encounter at Saturn wasn't with the planet. It was with a moon called Titan. Titan had been a mystery since its discovery in 1655. It was known to have an atmosphere, the only moon in the solar system with one thick enough to matter. But the atmosphere was so dense, so opaque, that no instrument on Earth had ever seen through it to the surface. Voyager 1 was sent on a close flyby of Titan, a very close flyby, closer than any other encounter in the mission. Scientists wanted every photon, every particle reading, every measurement the spacecraft could gather. What they got was both a treasure and a frustration. The atmosphere was real, thick with nitrogen and methane, with a surface pressure 50% greater than Earth's. The chemistry inside it was extraordinary. Sunlight was breaking methane molecules apart and reassembling them into complex organic compounds. Tholins, the same building blocks associated with the chemistry of life. But the surface remained invisible. And here was the consequence. The Titan flyby sent Voyager 1 on a trajectory that curved sharply upward, out of the plane of the solar system. Away from Uranus, away from Neptune, away from any further planetary encounters. By choosing Titan, Voyager 1 gave up the solar system and began its journey towards something much larger. For most of the 1980s, Voyager 1 just flew. No more planets to visit, no new targets in the camera's frame. Just the slow, steady drift outward, powered by a plutonium heart growing quieter every year. Then, in 1990, Carl Sagan made a request. He asked NASA to turn Voyager's camera around. It was not a scientific request. The cameras had already been powered down to save energy. Reactivating them would cost power the spacecraft couldn't easily spare. Some engineers pushed back. There was nothing scientifically useful to photograph. The inner planets would appear as tiny smudges, nothing more. Sagan argued for it anyway, not for science, for perspective. From 6 billion kilometers away, Voyager 1's camera took 60 frames across the inner solar system. Scientists assembled them into a mosaic, and in one of those frames, a single pixel, less than 1/12 of a dot on the image, was Earth. Sagan wrote about that image for the rest of his life. Every war ever fought, every empire ever built, every act of cruelty and every act of kindness, all of it had happened on that pale blue dot, suspended in a sunbeam. After the photograph was taken, the cameras were turned off permanently. They've been off for over 30 years. Voyager 1 would never look back again. For decades after the pale blue dot, scientists tracked a number they were increasingly impatient to see change: the particle count around the spacecraft. Inside our solar system, space is not empty. The sun breathes out a constant stream of charged particles. The solar wind that fills the heliosphere, a vast bubble stretching far beyond the planets. The boundary of that bubble, where the solar wind finally runs out of force and interstellar space begins, is called the Heliopause. Nobody knew exactly where it was. Nobody knew exactly what crossing it would feel like, or whether Voyager's instruments would even survive long enough to detect it. On August 25, 2012, they got their answer. The data was subtle at first. The count of solar particles plummeted. The count of cosmic rays from outside the solar system spiked sharply. The magnetic field shifted. Voyager 1 had crossed the Heliopause. It was now in interstellar space, the space between stars, the first human-made object in history to leave the solar system. The team at JPL cried. One of the mission scientists, Ed Stone, who had been working on the Voyager program since before launch, said it was the moment he had been working toward for 35 years. The signal confirming the crossing took over 17 hours to arrive at Earth, and still, the spacecraft just kept going. Voyager 1 is currently moving at roughly 17 kilometers per second relative to the Sun. That sounds fast. It is fast, faster than almost anything humans have ever built. And it is catastrophically, almost insultingly slow compared to the distances ahead. The nearest star to our solar system, Proxima Centauri, is 4.24 light-years away. At Voyager's current speed, it would take approximately 73,000 years to get there, and Voyager isn't even heading toward Proxima Centauri. In approximately 40,000 years, Voyager 1 will make its closest approach to another star, a red dwarf called Gliese 445. The closest approach will still be 1.7 light-years away, a near miss, cosmically speaking. By then, no one from our civilization will exist to track it. The languages spoken today will be as foreign as ancient Sumerian. Every institution, every government, every monument we've built will be gone. And Voyager will still be flying. In roughly 4 to 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, swallowing Mercury, Venus, and likely Earth. Everything we've ever built, every city, every museum, every grave will be vaporized. Voyager 1 will be somewhere in the Milky Way, still moving, utterly unaffected. Around the same time frame, the Andromeda Galaxy, now a faint smudge in our night sky, will collide with the Milky Way. The two galaxies will pass through each other over billions of years, their stars so far apart that almost none will physically collide. But gravity will reshape both into an entirely new galaxy, sometimes called Milkomata. Voyager will drift through this transformation without slowing, without burning, without even knowing. In about 10 trillion years, 1,000 times the current age of the universe, the last red dwarf stars will begin to die. The universe will enter what cosmologists call the degenerate era, a dark, cold landscape populated mostly by white dwarfs, neutron stars, and black holes. No new stars will form. The universe will grow quieter, colder, and darker with each passing era. Voyager 1, or whatever remains of it, will still be moving. Because in the vacuum of space, there is nothing to stop it. If proton decay is real, ordinary matter, including Voyager, will eventually dissolve into lighter particles over timescales of 10 to the power of 34 years. If it isn't, the spacecraft may persist almost indefinitely, outlasting every star, every galaxy, perhaps outlasting the physical universe as we understand it. That golden record, those whale songs, that Beethoven, that mother's voice, that child's first words, may be the last remaining artifact of everything that ever lived on Earth. The universe's only evidence that we were here. Here is the thing I keep coming back to. Voyager 1 has no mind. It doesn't know what it carries. It doesn't know that the people who built it are dead. It doesn't know that the civilization that launched it has changed beyond recognition. It doesn't wonder about its destination because it has none. It just flies. And yet somehow that makes it more moving, not less. Because we knew. The engineers who stayed up through the night to track it knew. Carl Sagan knew. The woman who heard a child's first words and decided that sound deserved to travel to the stars, she knew. They all knew that this machine would outlive everything they loved, and they sent it anyway. That, I think, is the most human thing ever done. If you're still watching this, genuinely, thank you. This kind of story is why I make this channel. If you want to see more deep dives like this, subscribe and hit the bell, because the next video goes somewhere even further than Voyager ever will. And leave me a comment with one thing you'd put on a golden record if you could. I read every single one.